Where did Oumuamua come from? Interesting question. Well, let's go back to the beginning of the story first. The discovery of this object named Oumuamua was in 2017 using data from the Pan-STARRS star survey by Verick et al. Using the telescope on Hawaii that you see pictured there. What they found was a small moving object that appeared as a single point of light, and this image on the right is focusing on that dot and allowing background objects to move. So this is a long exposure tracking the progress of this object across the sky, so picking out it as stationary and everything else is moving. And there is no sign of any sort of comet-like tail, and so this was probably not a comet, probably an asteroid. They worked out that it was 33 million kilometers from the Earth. That's 0.22 of the Earth-Sun distance, one astronomical unit, or 85 times the Earth-Moon distance. But at this point, it was already heading away from us, getting further away, having passed the Earth and passed the closest approach to the Sun, the perihelion point, some 40 days earlier. So we'd almost missed it. Now, as is common with these sorts of discoveries, it's then possible to look back in the data that's been previously recorded and locate the object where it had not been identified in a so-called pre-covery image, and we can also track it going into the future and thereby compute the trajectory that you see there from before the discovery on the flyby through the solar system. And you can also look at the brightness of the object, and this is a brightness curve starting off at a very low level of magnitude 34 and peaking at about magnitude 19, so still fairly faint, at beyond the reach of most amateur telescopes, that's for sure. But it's got this weird double peak at the top, which I need to explain. Now, what happened here was it came close to the Earth, and as it got close to the Earth, we saw it as bright. It was obviously brightening up as it came towards the Sun and the Earth to start with, and then it passed by the Earth and started moving away from us, and so we saw it as fainter, and you got that middle dip. But then it started getting closer and closer to the Sun, and so the amount of light hitting it went up, and so it became visibly brighter again, before receding from the Sun and the Earth and returning back to its original brightness. That took a period of about 3 years on the inward side and then about 3 years on the outward side. So this is about 6 or 7 years worth of observational data. Now, when you looked at it in real time, it showed this very interesting pattern of brightness that was varying in what looks like a cycloid curve. You can see the animation at the bottom, and it's suggesting that the object was tumbling and very long and thin, a cigar-shaped object. We're not entirely sure of the size. It could have been as small as 100 or as long as 1,000 meters, and somewhere between 35 and 167 meters wide. So a small object, but we're not entirely sure how big. What was interesting also about it was the trajectory as it moved around the Sun. It wasn't following a planet or indeed an asteroid-like orbit. It was behaving a bit more like some small comets do in a non-gravitational orbit. So it was deviating from the standard Kepler's law-based orbit. This is usually caused by a combination of the heat from the Sun hitting the object, warming up one side, causing the release of volatile gases, melting the ice, and causing jets of material to burst off the surface, and that can create enough thrust to push a small object off course. Plus, it warms that side, and if the object is rotating, then the warm side rotates away from the Sun and re-radiates energy in a different direction. It's called the Yarkovsky effect, and that can push the object off the standard trajectory as well. So there are a number of reasons for this, but this seemed to be suffering all of them, and yet showing no comet-like tail. So the lack of a tail really sort of didn't fit with the source of this deviated orbit. And it led many people to speculate that this wasn't an asteroid at all, but was an alien spacecraft. To the extent that the Search for Extraterrestrial Intelligence, SETI, turned its telescopes to the object to listen for radio signals, including the Allen array there and other telescopes as well. But they didn't find anything. So if this was a alien space probe come to have a look at us, it was being radio quiet on the way past. Now, follow-up observations of it, such as the photograph at the top right there, revealed that this is actually a small object and very bright, very shiny indeed, reflecting perhaps 10 times as much light as many dark objects. Some of the objects, such as the moon, only reflect about 10% of the light, maybe even less. And this was definitely on the very shiny side. Now, we've seen that before. Things like Pluto is very shiny and reflects a lot more light than anyone was expecting. And it's often the case that we guess the size of something based on the brightness and the known distance. And that was the case with Pluto. It was much smaller than anybody thought because it was much shinier. And so that's probably what's going on here. And it's probably at the smaller end of those size estimates. Now, it's probably very shiny because it's covered in ices. That's the usual reason. And in this case, it might be frozen hydrogen. That could explain the outgassing without creating a tail. A tail would be created if you had water ice or methane or ammonia being boiled off the surface, because it would soon cool and freeze and create ice crystals, and those would reflect the light, a tail. But the hydrogen wouldn't cool enough to freeze out again and would be blown away by the solar wind, and we wouldn't see it. And so that's the explanation that was proffered for that. Now, the image also shows a red color there, and that's believed to be similar to many outer solar system bodies. And we put it down to the presence of chemicals called tholins. Those have been manufactured in the lab in those vials that you see to the right there. And these are carbon, hydrogen, nitrogen, oxygen, organic materials that are the possible chemical breeding ground for the chemistry of life. So very interesting indeed to see it on this object. Now, it entered the solar system very, very rapidly indeed, doing 26 kilometers per second, picking up speed. And as it passed the sun, that speed had increased all the way to 88. And it had such momentum that the sun wasn't able to capture it in any way. It deflected the orbit. You can see it's a near straight path on the way in, bends round because of the gravity of the sun pulling on it, and then escapes, tending towards a pretty straight path as it zooms away from us. And it left at more or less the same speed that it came in, 26 kilometers per second. So that's a tremendous speed, and it's 10 times as fast as your typical orbital velocity of anything in the outer solar system, such as Pluto going around the sun. That's why it escaped. It was way more than it needed to get away from the sun's gravity. Now, we're here to talk about the origin of the solar of this, and one of the possibilities is that it came from a molecular cloud. These are clouds of gas and dust out in space, several light years in diameter, truly huge, relatively low density, but very, very cold in the center. All that dust blocks the pervading starlight from being able to get into the middle of the cloud. And so the temperature can be as low as 30 degrees above absolute zero, 30 Kelvin. And at that temperature, it's hypothesized that hydrogen can freeze out and you get lumps and small bodies of hydrogen ice forming. And maybe those formed in some molecular cloud, and gravity would have then started them orbiting around their common center of mass, and perhaps a near miss occurred and one of them got slung shot if that's a word, out of the cloud and found its way to the solar system, and we observed it as Oumuamua, hence explaining the presence of that volatile hydrogen and the outgassing without a tail. But there is another possibility, and I came across this paper on the dynamical history of the interstellar object Oumuamua. You can see the names of the author and the contact details and so on. I'm going to post the link to the paper in the description of the video at the end. And this was an example of a really good study looking to see if they could figure out where it had come from. Now, what they did was take survey data of the position and motion of 200,000 star systems within 200 light years of the sun. That's a lot of data. And they compared the trajectory of Oumuamua and the sun against each of those 200,000 stars. They didn't compare everything with everything else. That would have been completely mathematically not feasible. What they did was make a three-body problem 200,000 times over. So it took each object, the sun and Oumuamua, and computed the effect that the sun and the individual object would have had on the passage of Oumuamua to decide whether that other star was relevant or not. And a lot of them could be ruled out as just not contributing very much to any deflection. In fact, it allowed them to drop the number from 200,000 to just about 100 relevant stars. So a much more tractable problem. And the second step was to look at those 100 stars. And a manual inspection of the survivors of that filter was able to further reduce it down to just 57. And this was because within that group of 100 relevant stars, many of them were components of multiple star systems. A good example being Alpha Centauri with the components A, B, and C. So that's Rigel Kentaurus, Toliman, and Proxima Centauri, to give them their names. They're all close enough to each other that we could treat them as one body and forget about the fact that they're actually separate objects for the purposes of computing the overall gravitational effect on the path of Oumuamua. So we could replace all the multiples by a single combo point and get down to just 57. This is a much more reasonable sort of problem. So with the remainder, you could then work out, taking their individual mass of each system into consideration, which had the largest effect, and rank them in order as having greater or lesser effect on the trajectory of Oumuamua. And of course, the winners of this process turned out to be the most massive nearby stars, which are the Alpha Centauri system, adding the mass of all three of them up, and the mass of the Sirius system, Sirius A, and its little companion, the pup. The others are all much, much less massive, small red dwarf stars with a fraction the mass of our sun, and the mass, for just to make it clear, Alpha Centauri and Sirius add up to more than double the mass of the sun each. And so these much smaller red dwarfs or even brown dwarfs that are a tiny fraction of the mass of the sun really don't contribute very much to the deflection. And so we could largely discount quite a few more in the analysis. And where this takes you is that there were just 7 stars that came close enough to be of interest. They came within 3 light years of the possible trajectory. And so these are the ones that are going to have substantial effects. One came within 0.13 of a light year, and you can see which one that is. It's in red at the right-hand side of the diagram. The diagram has time going on the horizontal axis from now at the right to 3 million years ago on the left, and it has the distance from Oumuamua as the track of each of those objects. So you can see they all came fairly close, but the one labeled HIP 3757 came very, very close indeed. Now, the other part of the analysis was to look at the relative speed of that star and Oumuamua at the time. And the speed for that closest approach we'll see in a moment, but it was very, very high. On the other hand, there were 4 of those encounters that were fairly low speed. And low speed is important because if you're going to be ejected from a solar system, having started with orbital velocity, you might pick up enough speed to escape the gravity of the star, but it's very unlikely you're going to pick up much more than that. And so you would likely depart the star system with a relatively modest amount of remaining escape speed. And so that's the sort of thing that we're looking for with these low speed encounters. So just to look at that close encounter for a moment, that was the star HIP 3757, and Oumuamua passed it 120,000 years ago, but it was going very rapidly indeed, 185 kilometers per second of relative speed. That's many times faster than the encounter with the sun. So this was a flyby. This enters the region of space near the star and just whizzed past it. It couldn't really plausibly have been ejected from the system. It's just going too fast. However, the better example was this one. 820,000 years ago, Oumuamua passed close to Gliese 876, designation in the Hipparcos catalogue 113020, and a much more sensible velocity, just under 4 kilometers per second in this simulation. And so that is much more plausible as actually not a flyby, but an exit event kicked out by gravitational interactions within the star system. So what do we know about Gliese 876? Well, it's a red dwarf star. It's in Aquarius. You can see it on the star map there, just next to the Delta star. And it's 16 light years from the sun, so relatively nearby. And so if Oumuamua came from the realm of Gliese 876, it took 820,000 years to do so in all probability. Now, we know that Gliese 876, this little red dwarf star, has its own family of planets. We know of at least 4, 1 small one and 3 giant ones. So maybe it was the interaction of those planets that led to Oumuamua being hurled out of the system. So that planetary system, we know the orbits and we know a reasonable amount about each of the planets. We've got the orbital map here showing that they're orbiting quite close in the case of D and further out for C, B, and E. Now the labels are the order of discovery. So B was discovered first, then C, then D, then E. I don't know why they don't start with lowercase a, but never mind. And what we know about them is that B, C, and E are in a gravitational tug of war, making their orbits slightly elliptical. This is exactly what happens with the innermost 3 moons of Jupiter, and it keeps them in those elliptical orbits and a tug of war. And it's entirely possible that something to do with the gravitational interactions of these 3 planets could be responsible for kicking Oumuamua out of the system. So what do we know about the planets? Well, taking them from the inner realm outwards, we start with 876d, and this is a super Earth planet, 6.8 times the mass of the Earth, likely to be rocky and baked very hard indeed, because it's orbiting 50 times closer to the star than we do at 0.02 AU and going around every 2 days. So it's probably also tidally locked, keeping one face towards the star. And even though the star itself is a relatively modest 30% or so of the mass of our sun and 3,500 degrees or so, that's going to be hot, 350 degrees centigrade Celsius. It's going to boil the water off the surface. And if it's tidally locked, one side will be very hot indeed, and the other side may be a little cooler. interesting to learn more about this one as our studies improve. Unfortunately, these planets don't transit in front of the face of the star, so we are unable to actually look at the case of light being filtered through their atmospheres, as has been done with other worlds out there, other exoplanets. Moving on, the C planet is about the size of Saturn and is 13% of the Earth-Sun distance, 0.13 AU from the star. Now that's just right to be in the habitable zone where liquid water could exist at the sensible sorts of temperatures. But it's not going to happen on a gas giant planet like this, although there is the intriguing possibility that all the gas giants in our system have fairly significant moons, and so there's no reason why this one would not have a moon, and that moon would be in the habitable zone. So that's very much worth investigating further. 876d, this is a very large planet indeed. It's more than double the mass of Jupiter. I think it's 2.36 times the mass, in fact, a gas giant, and orbiting around 0.21 astronomical units, so about twice as far out, and therefore the temperature at this distance would be likely to be quite chilly. But again, a bit of atmospheric warming on a moon orbiting this giant planet, and a giant planet might have giant moons, who knows. And finally, 876e. This is rather like Neptune. It's an ice giant. It's 16 Earth masses and is around about a third of an astronomical unit in a 124-day-long orbit going around at the outer edge of the known planets. But I'm sure that we'll find more as we learn more about this interesting star system, and the possibility that it ejected Oumuamua out towards us. It will also be fascinating to learn more about Oumuamua, and so scientists have considered the idea of sending a probe. Now, the problem with that was we saw it on its way out of the solar system, so there was no warning. We had no time to get anything ready as it was coming in, not really any time to launch a probe towards it, and it's moving very fast. Trying to catch it at the speed it's doing would be very difficult indeed. We would need to travel twice as fast as the New Horizons space probe that went to Pluto, and that would need every trick in the book, including a slingshot round Jupiter, a slingshot round the sun, diving as close to the sun as possible and picking up as much gravitational slingshot as we could, and it would still take 25 years to get close to catching it. So probably not going to happen, but maybe we should be ready for the next one and have a probe parked in space, perhaps at one of the Lagrange points, where we park quite a number of our space telescopes, such as the James Webb and Gaia, things like that, and have a probe ready to go. Perhaps even we could put it in orbit around the moon or something and ready to hurl it off in the right direction to catch the next interstellar visitor. That way we might figure out whether the sci-fi stories are true and that it was an interstellar probe. More realistically, perhaps we'd find out what it was made of and be able to figure out whether that hydrogen ice idea is a good one. And just before I leave you, I'll just point out that the interstellar probe idea isn't a new one, and people made great parallels between Oumuamua and Rama, as in Rendezvous with Rama by Arthur C. Clarke, a really good read if you get the chance. And the shape of the Rama spacecraft was that long and thin cylinder, and so it had all the hallmarks, and I just find that rather amusing, so I thought I'd just leave you with that one. So thanks very much for listening, and well, I hope to hear that we've figured this puzzle out in more detail in future